Today we're going to talk about how we can actually work with gears if we want to have multiple gears interacting with each other and have multiple stage of gear ratios. So whenever we have at least two gears interacting, it counts as a gear train. And when we want to have multiple stages, we could just call it multi-stage gear trains. And what we're going to do is we're going to have pairs of gears, so a pinion and a gear. But with each gear that we have, we're going to also have a pinion that shares the same shaft as the gear. So I'll draw that for you in a little second. So we're going to say that we have our input device. Let's say that we have a radius of 1 foot. And that's going to interact with our second. So here we have a pinion. Whenever we have the smaller gear, we'll refer to that as a pinion, just to keep track of what's going on. And we'll say that the pinion is going to drive a gear. And on the same shaft as that gear that has a wide range, so we'll say R2A is equal to 5 feet. On that same exact shaft, we're going to have another pinion. And this one is going to have a diameter of 5 feet. Let's say 1.5 feet. Not 5 feet. The large one is 5 feet. So that will be R2B. And then that can drive another gear. So this will be a 2-stage gear. And we'll go through what's happening and see what's going on. So let's say R3 is 6 feet. So we'll start off with our first pinion. The omega of gear 1 will be set at 20 radians per second. Because we have larger gears, we expect that our speed should decrease and our torque should increase. So R1 is set at 1 foot. And our torque 1 is set to 1 foot-pound force. Now, for omega 2, we have that omega 2 is based off of omega 1 and the ratio of our radii. So we can say omega 2 is based off of that 20 radians per second that we start off with. And omega 2, if we look over here, we would see that omega 2, we would bring this over here, would be equal to omega 1 times R1 divided by R2. And so let's go through, and we'll say that this is times that initial 1 foot. And we'll divide it by our 5 feet, because that's the radius of the gear that's interacting with that pinion. And we get 4 radians per second. Our torque 2 we can do in the opposite manner. So we'll take that original 1 foot squared, or 1 foot-pound force. And we're going to divide by 1 feet and multiply by 5 feet. So that ratio is flipped when we go through this. And that gives us 5 foot-pound force. So as we expected, we saw that our radius increased and our torque decreased. Now, for our third set, now what we're going to do is we have that this little pinion over here is rotating at that same 4 radians per second. And I see that I have a helpful spell adjusting, which should not be turned on, but it is, but we'll live with it. So when we want to calculate this, we'll take that starting 4 radians per second. And now we're going to interact with the smaller pinion that's on that same shaft. And so we can divide by 6 feet, and we end up with 1 radians per second. And our torque 4 is again going to start off with the torque that we had from before, because that's constant for the device. That'll be that 5 foot-pound force. We're going to divide by that 1.5 instead of multiplying, and we'll multiply by 6 feet instead of divide. And that gets us that we have increased our torque from 1 foot-pound force to 20, and we've decreased our velocity from 20 radians per second to 1 radian per second. So that's how we go through a gear train. And for this example, we went through very simplistic versions of looking at the gears, where I've been drawing them as circles. We took that statement saying that we have the force working in, force going out, and it's actually not as simple as that. So